Okay, so this talk is about a practical use case of a real application that has a problem. It's just as the title states, is IO contention. Okay, and the solution that we propose is a runtime solution applied during the application execution. Okay, given that the application has an important role, the idea is just first to describe the application and then motivate the problem and then see what is the solution that we apply. Okay, so the application is called Epigraph, was developed in our group many years ago, more than 10 years ago. We tried to model the influenza. There was an outbreak at this time, the A class. So we developed an agent-based model that is parallelized with MPI. Agent-based means that we simulate every single individual. We do something like a virtual city where you simulate every individual with the characteristics, how they move, how they interact with other individuals, and of course, if one individual is infected, how the contacts are made and how the transmission is done of the infection. We originally worked with influenza, but then during the COVID-19 pandemic, we quickly adapted to that, and we have collaborated in Spain with the Ministry of Health, and especially with the ECDC, that is the European Agency for Disease and Prevention. I think that the States you have the CDC, here we have the ECDC, that is the equivalent in Europe, and they ask us to simulate different vaccination scenarios, which basically is have a vaccine. Let's see what is the most effective way for applying that, especially elderly people or young people. And we tested, we were one of the teams, of course, there were more teams involved. This is the Epigraph webpage, by the way. And now we are not working so much in COVID-19. There is another round now this year with the RSV virus for infants. Okay. Anyway, this talk is not about epidemiology, just put the things in context. Now going more specific. Okay, so what we have is we have a sparse data structure. Okay, where the interactions are time dependent. So what we use are graphs. Okay, and the connections that we can see in the figure. So let me try to see. Yeah, here for instance, this individual we have different time slots. So during work time, for instance, if it is a worker, there is interaction with the neighbors here. This interaction is extracted from social networks, so it's quite try to be as much realistic as possible, sparse in memory. And then during, for instance, after work, during leisure time, there are connections with other individuals, okay, that represents physical connections between them. And then at night, if the individual has a family, there's a family time with all the connections with the family members. You can just imagine, no? What we do is we try to see how the disease is propagated. In this case, was COVID-19. We just loaded from many social indicators. In this case, it's in Madrid. So we allocate each individual in a different part of the city, and we load indicators like gender, age groups, contacts with the number of children per family, and also social indicators and wealth indicators that, at least in Spain, I think that in all the parts were relevant for the propagation. Okay, so the results here is just for one scenario that is Madrid, with 3.5 million individuals simulated in MPI. We use up to 144 processes, and we have larger scenarios with up to 20 million individuals, 90 cities in Spain, and hundreds of cities in Europe. Okay, so this for us is just a medium-sized scenario. Okay, so what's the behavior of the application? Okay, we have different phases here. Each phase is parallel. Okay, so have different cities, a partition per cities, which is good because we can scale quite well with the number of cities are quite independent. And then there are infection phase when the infection is propagated, updated. It's a stochastic simulator, so we need to generate random numbers. Then there are different vaccination policies. Now you can see if we vaccinate one individual, you get immunity. So the probability of being infected or transmitting the infection is smaller. Okay. So these two phases are mostly CPU intensive. Then there is a transportation for moving individuals between different cities. Okay, this is more communication intensive. And then we have a IO phase just for not checkpointing, but saving periodically the system state in order to reproduce the simulation. Okay, so we repeat this across the time. And here I have an example of the CPU time, okay, in blue. For each, is the average of iterations per simulated day and the number of infections, okay? So we can expect what we have is the larger number of infections, the larger computation time, the CPU time, because we need to do more computations. COVID-19, as you know, there are infection waves. So what we have is just a low incidence scenario. This case was the Omicron that was a very big infection wave. So there is a huge amount of increase of infections and then a sharp, in this case, sharp decrease of infections back to the normal situation before Omicron. So what we see is that the CPU is barely follows the number of infections. Okay, have to be careful. I will use this figure. And what we represent here is the simulated day. Okay, but this is not the execution time. Actually, as we see here, these days are executed very quickly because the CPU iteration time is very small. This takes the largest part of the simulation, and what we call the second phase is also executed very quickly. Okay. By the way, just introducing thing, maybe you can think, okay, this is an application guy, but in our group we have developed other more performance-oriented runtimes that I will introduce just shortly. Okay. So what do we have about the application behavior? Basically, as we said, you alternate CPU, communication, and I/O. Okay, I'm going to include communication inside the CPU part in these figures. So when we are in the first phase during this outbreak, we see that the weight of the CPU phases is much bigger. So the I/O is very well spaced, as we see up here. But then when we have a low incidence level, then the CPU phase is smaller, and we have the I/O phases that are happen more frequently. Okay, the duration of the I/O phases is barely the same because we just write the same amount of data every time that we do the I/O. Okay, but the difference here is the frequency. Okay, here the I/O is more spaced and here is more frequent. Okay, so let's go and see what happens in the system when we do that. From now, just shifting to the performance point of view. Okay, so here what we show is that for the different number of simulated days, the I/O bandwidth per each I/O operation are several runs. It's not one execution, but the execution, I think that 5 different runs. And we have something interesting here. At the beginning is we get at the beginning a very high, much better I/O bandwidth than during the rest of the execution. We think that corresponds to this part, by the way, at the beginning. We think that this is because of the file system buffering. In this case, we use a BGFS file system, spiral file system. Probably because of that, you can just keep a higher ratio of accesses in the hit ratio in the buffers, and then the bandwidth is barely constant, okay, during the execution. In other words, the effect of having less or more intense I/O is not noticed when we run one single application. In other words, BGFS is able to absorb all the I/O operations without degrading the performance, okay? But as I mentioned, this topic is performance degradation because I/O conflicts. When do we have this problem? When this problem arises, okay? The problem arises when we execute multiple instances of the same application, okay? So what happens is, being practical, epigraph is an stochastic, as I said before, which means that the solution slightly changes during each run. So in order to provide an accurate solution, not us, but the ECDC asked us to run multiple times the simulation, up to 100 per scenario, which is quite a lot for us. and then do a statistical analysis about the results, no, the different things that we're working for them. So this is the workflow that we have in Epigraph. And what we see in this workflow is that there are different stages, and I will just focus on this one. That is when we run the multiple instances of the program. Okay. In our case, we run in these experiments 8 instances, 8 different applications at the same time. And what do we find? What we find is that in the second phase that I mentioned before, that is the second phase is when the I/O operations are closer, then here running 8 different applications, this is application number. Here what we see is that there is a I/O performance degradation, okay? And this is because we have the same pattern, doing the same operation, sharing the file system at the same time, and with very short spaces within the different applications, okay? This doesn't happen in the first phase, but it happens in the second one. Okay, so this is the problem that we want to deal with. Solutions to this problem, okay, they are doing intensive I/O. One option can be to reduce the number of applications, but it's not good. Okay, we want to maximize the file system. Of course, we want to optimize the I/O. Another thing that we done in our experiments is do I/O bandwidth capping. We have modified the MPI to reduce the bandwidth and apply that. That could be another solution. But in this work, what we do is we evaluate, change the application behavior by dynamically changing the number of processes. That is, we call malleability, application malleability. Okay, and how do we do that? Well, for doing that, we use a runtime that is called FlexMPI that was developed. This is the second software that I mentioned before. This is not application, just a runtime that provides dynamic capabilities to MPI applications. So if you link with that, the application can dynamically expand, increase the number of processes, and shrink, reduce them. And also, the data is automatically distributed. And we also, on top of that, we monitor the application. So we can collect different performance metrics from them. Okay, so this is the runtime that we integrated Epigraph with. And then here's an example about how we do. Just mention that we basically wrap the MPI calls. This is why wrapping the calls, we can monitor the weight, not only the CPU, but all the CPU phases, that is the kernel, but also the MPI calls, which are the I/O time and communication times. And there are some extra code that we need to put. So it's not completely smooth, the integration with FlexMPI, okay? But when it's done, we can run the application transparently with these dynamic capabilities. And okay, so on top of that, what we use is FlexMPI use PAPI library to use a measure of hardware events, okay? So we can measure flops, we can measure cache misses, memory accesses, etc. In the context of this work, we just measure the I/O time. We focus on the I/O. We measure the I/O time of the MPI libraries that you use for that. Okay. So the last piece, just to put everything in context. Okay. So we have now an application Epigraph that is malleable. Okay. What do we do with that? Okay. So the next thing is we were coordinating a European project that is called Admire. Maybe some of you already know. In Admire, the idea is that we have monitoring at different levels, but the idea is, okay, let's develop a central controller that, okay, the name maybe is called intelligent controller, but it's a kind of central controller that collects all the system information from different monitoring sources and makes holistic decisions about, for instance, deploying out file systems or applying a malleable aware application scheduling. I mean, changing the size of the application during the execution. Okay, so the application Epigraph is here, run with FlexMPI, run with a monitoring library. So we have all the information here. The information is connected with a monitoring controller that is able just to collect information and work with it, and then an intelligent controller that makes the decisions about, in this case, if we are going to expand or reduce one of the applications, okay? Then on top of that, we have models and SLAM environment when we run the programs. Okay, so this is the framework where we are working with. And the idea here is just to test as a proof of concept one idea for avoiding this I/O contention. Okay, so this is an example about the dynamic capabilities of epigraph. Here we have, this is the simulation time, okay, and this is the process. This is not exactly the one that we use in our experiments, but it's, I think, a nice visual example. So have 5 different processes originally. Here we represent the iteration time, okay? And at a certain point in here, we increase the number of processes, going from 5 or 6 up to 15, okay? So we can see that now there is a higher, the workload of the program is distributed, okay, across all of them, and it's not perfect because, as I said before, epigraph has a sparse data structure, so it's not easy to balance, but it's barely balanced. I mean, the iteration time per rank is barely the same. These have the same example, but changing from 10 original ranks until here and expanding to 15. Okay? So the idea is that the intelligent controller can tell the application, okay, now you expand, now you shrink. Of course, this is not for free. There are some overheads. We need to redistribute the data and create and distribute processes every time, okay? But at least we have another dimension in the optimization program. We can just change the application behavior, okay? So what is the solution? The solution that we present in this work. The idea here is, okay, we monitor the application. Okay, so let's, when the application is executed, is here, now have epigraph with Flex MPI. Flex MPI collects the performance metrics, sends the performance metrics to the intelligent controller, so the intelligent controller collects them, and at the same time as the I/O operations that are done. And the metrics are placed in a storage. We use Redis for that. When we place, it's in memory. And then offline, we develop a model that is a performance model of about the expected I/O bandwidth that the application has for every run of the program. In this case, it's a quite simple model that takes into account previous executions of the same instance, okay? The idea is now to reuse the model, okay? So one approach could be, maybe you're thinking about that, is, okay, you have the model, something that is called intelligent controller, so maybe it's a bit intelligent. So maybe it's able just to see if there is a performance degradation, and then tell the applications to change the size to avoid that, okay? This is one approach, but in this work, we follow a completely different one, okay? The idea is that instead of going into a centralized mode, when the intelligent controller decides everything, we delegate on the applications about what to do, okay? The advantage of doing that, okay, is that first of all, okay, the intelligent controller is centralized, but is parallel. So in our experience, we didn't find a bottleneck regarding this connection, because in the end, there are not many applications running at the same time. We can deal with hundreds of them that are the usual number, at least in a medium-sized cluster. The problem is the monitoring metrics. When we monitor the application, we collect a lot of metrics. So we are running, for instance, in our experiments, 8 of them. There is a lot of information that has to be processed. And this could be a problem in terms of volume of data. So in our approach, the model that was calculated before is uploaded into the applications. So each application is responsible of comparing its performance with the one of the model and making a decision about that. So it's a decentralized decision-making procedure. Okay? So let's go now to see what is the effect of that. Just let me check the time. So when we are here, the problem again is here where the I/O operations are more intense. What we do, okay, it's a big chart. The model is this green line, that is the expected I/O performance. And the blue dots are the real ones that the application is monitoring. When I say application, actually is Flex MPI that is linked with the application, all the control mechanisms there. Okay, and what we do is we collect the execution time, the TP of each I/O accesses, and then we have the one of the model. So, for instance, in this point, this is the real one. This one is the model. And this is the difference, okay? The delta between the real and the model. So if delta is reduced, it's good. We are good because what we are doing is we are approaching to the maximum theoretical one, or not theoretical, empirical one, okay? The problem comes here when there is a performance degradation about the I/O bandwidth. So what we do is we define a trigger point, okay? Once we get the maximum value, we detect when we reduce it a certain percentage of the value. And this reduction has to be sustained. Sustained means that we need to keep it for several simulated days, not in one point, because maybe it's spurious, maybe it depends of other things, other applications, but has to happen in several times, okay? So when that happens, then we call it reconfiguration time. So they have to make a decision. So for instance, here we have a practical example of 8 simultaneous runs with different outputs. Okay, this is different outputs, sorry, different performance values. And we can see that in our experiments, all of them reach at the same point, barely the same day. Okay, this is because we are exactly running the same application. Of course, there are some variations because it's a stochastic, there are some randomness also related to the access, but in our experiments, most of them reach the same, barely the same time of the execution, okay? So what do we do here? Okay, we want to reduce now the pressure on the file system. And the idea is that a certain percentage of the applications, I want just to decrease the number of processes. So we decrease the number of processes, we increase the execution time, and we change the I/O access pattern. That's the idea, okay? So here are the results. This is during the first phase, here the malleability is not applied. So all the bars here, this is the application ID, 8 applications. They should be the same, okay, are real values, so it's not exactly the same, but we see that they're quite similar in most of the cases. And here, that's the interesting thing, in the second phase is when we apply malleability. In two cases, in one case, is 25% of the applications are malleable, is this round bar, and in the blue is 50%, that is out of 8, okay? And what we found is that by means of malleability, the I/O pattern is changed, and because of that, the I/O bandwidth is increased. As we can see here, both for malleable applications that are this kind of dashed bars, and also for the solid ones that are the originals, unaffected. They don't receive malleable changes. They are not reconfigurated, okay? So in overall, we are able to improve the I/O bandwidth in the second phase between a 7% and a 14%, okay, applying this approach. Okay, what is one of the trade-offs? One of the trade-offs maybe you can think is, okay, if you reduce the number of processes, maybe you are degrading the application, so it's a penalty for the application. But in this case, this is not exactly true because, as I said before, the application here scales very well, have a very high CPU times. So here they have a very good scalability. But in the second part, the CPU time is not dominant, which means that even if we reduce the number of processes, the execution time is not increased because, for instance, we save communication time because we are involving less processes in the communication processes. So this malleable action saves, in the end, saves use of resources, does not degrade the application, and on top of that, avoids the I/O contention. Okay, so just to summarize, we think that malleability, when we say malleability is dynamically changing the number of processes, we think that is a promising direction. It's not something straightforward, especially because it's difficult to adopt, okay, and standardize. So there is a lot of things here going on. Was on Monday a Vero Feather, maybe some of you were there when we discussed these things. But the advantage is we can improve the application from the CPU perspective. In this work, also from the I/O perspective. It's complex to apply. We need extra additional information like monitoring data. But if we do that, we can have, for instance, some also productivity because we can work not with runtimes as in this work, but at algorithm level, applying policies, which is, I think, interesting as another research direction. And we can improve the performance. And now, in this case, applying it to the I/O. Okay, so that's all. Thank you for your attention. It's here, this, yeah.
Are there any questions?
Clay, I have a question.
Yeah, go ahead.
So on slide number 6, I was wondering if you try to overlap the I/O with the compute part. So you are running, I think, thousands of iterations, right?
Sorry, say it again. I didn't hear you.
Slide number 6.
On slide number
slide
6.
number 6. Let me go back to it. Yeah.
If you overlapped the communication or the I/O with the
No, the communication is not overlapped. So we have CPU and then communication, which means that it's synchronous communication and then I/O. I/O is a parallel I/O. Okay, we use collective MPI calls for the I/O.
So could you try that non-blocking communication primitives like I send or I receive kind of thing, and then see the difference?
Yeah, it's a good idea. With this application, we haven't do that, but it's in the to-do list because one of the things that we have done, as I mentioned before, is I/O bandwidth capping. And this I/O bandwidth capping limitation, we can limit by the intelligent controller, can be applied to asynchronous I/O. So yes, this could probably reduce the. The only thing is that for doing that, given that we are changing the state, maybe we need to do an extra memory just to. But following your question, another option that yes we have tried is to, instead of just writing into the parallel file system, we use an intermediate file system, an ad hoc in-memory file system. Okay, this in our case was Hercules that was also developed in our group, and with the ad hoc file system that is in memory, we don't have any contention issue because the bandwidth is just very, very high. Yeah.
Okay, thank you.
Thank you.
Are there any other questions?
Yeah, in my experience, measuring I/O is actually hard on a compute cluster.
You mean because of variability?
Because you're not alone, right? So
Yeah.
if you're measuring your application alone,
Yeah.
then
That's.
I mean, as I said,
Absolutely.
it's hard. So
Yeah.
so who's going to step back actually? I mean, the variation in bandwidth could not be due to like your application being replicated, but due to other applications hogging the network or hogging the I/O system. So who decides which application has to step down or reduce its I/O?
Yeah. So in our experiments, what we did, because I absolutely agree with what you're saying, what we did is just to repeat the experiments many times and also waiting for periods where the system is not heavily used, because you're right, if you have an I/O intensive application running at the same time, can kill your performance. I completely agree. So I think that your question is being practical, no?
Yeah.
If you have in this kind of environments, so probably in this kind of environments, maybe it's a kind of pet, maybe what you have to do is that if you're lucky, fine. But if you have another application running at the same time, maybe some of these approaches doesn't work because maybe the degradation is much bigger. But yes, it's difficult to be deterministic in these environments. Yeah. Just only one thing is, I think it's worth mentioning that I have a second talk in another workshop when we analyze this problem, but from a performance point of view, using Hercules and more based on maximizing the performance, not without I/O contention. Just in case. It's interesting.
Maybe I missed it, but how does this interact with the scheduler?
Yeah. So this for us was a very one of the hardest part of implement because SLAM has not support for that, but we found a trick for doing that. So what we can do is that we can allocate resources, and we found a way just to release them from the SLAM. So without changing the SLAM. And then if this is not example, but for instance, we also did test, you have the same user has another application, we can just give these resources to another application of the same user. But if it is a different one, no. Actually, at the beginning of the project, SLAM has a support for that. So we ran the test and everything was nice. And then they changed the version and discontinued. So we were completely, and we spent nearly 1 year trying to figure out how to do it. And the solution that we have now is not perfect. It's not perfect. There are other groups working on that, but at least provide some flexibility for doing that. Yeah. But this is a challenge. Yeah.
Have you looked at other schedulers like Flux or?
Not yet, but this is another solution. Yeah, just to go. But if you are, in this case I didn't mention, sorry, it was a production cluster that is not ours, is in Torino University, HPC for AYA. No chance of changing the schedule. Yeah. Another alternative to do simulation, we use Elasticine as well, but simulation is a completely is a different area. Yeah.
Let's thank our speaker one more time.